And thank you all for being here. So let's get to it. Uh, so as a motivation, I'm sure we all know group theory is probably one of the most used algebraic objects in the whole field in math. And one of the reasons for which groups is so important is because we can talk about the representations. And these representations allow us to describe symmetries of really nice algebraic objects. For example, vector spaces, commutative algebras, etc. So it is really nice to work with symmetries and thus study these representations of groups. Actually, you have whole courses on this topic. And moreover, when you try to push yourself to the non-commutative side, actually you also get to work with something similar to groups, but not quite the group itself, with something that is called a Hopf algebra, which is just, we could consider it a generalization of the concept of group so that the symmetries behave well. When I say symmetries, I refer to representations. And in this case, actually, we talk about quantum symmetries in this non-commutative setting. So basically, what I want to remark here is that representations of groups are nice. And I briefly recall the notion of a representation of a group, which is just basically a vector space with a group homomorphism going from G to the space, to the group, actually it's a group of linear automorphisms of that vector space. And what is nice about the representation, well, there are a lot of things that are nice about representations, but one of the things which is nice about this is that if you take two representations of the group, then you can consider the tensor product, of course, as vector space. But it turns out that that vector space, that tensor product, is again a representation of the group. And this is a nice feature that is held by groups, and not many other algebraic structures in math can say that, hey, the tensor product of my representations is again a representation. Another good thing is that if you take the base field and you tensorize over a representation, you recover the original vector space. And not only that, but in the category representations, you also get, well, the same representation. So not only you recover the vector space, but the representation itself. So inspired by this, we define what is a monoidal category, which is basically a category with a bifunctor, which will resemble the tensor product of vector spaces, an object, which we call the unit, which will resemble the base, the base field in the vector spaces, and some natural isomorphisms, which just ask you technically that you have an associativity, that the unit is actually a unit, and some conditions that you have to have in your category in order to everything here to work. So two basic examples of monoidal categories are, as I was just saying, vector spaces, where the bifunctor is the tensor product of vector spaces, and also, as I was just mentioning, the representation category of a group, which we call RepG. So these two categories are very basic examples of monoidal categories. But when we do group theory, we also have the notion of group action, which is basically the notion of module over a group. You have an action, which is an action map that goes from G times B to B, and you can work with this. Of course, this category, if you consider category of actions of G modules, you get another monoidal category. That is, if you take those modules, then you do the tensor product, and that's again a module. And if you tensorize by the base field, you recover the original G module. And of course, we don't do the distinction between representations of a group and actions of a group, and that's because they are basically the same. That means that RipG and Gmod, these two categories, which are monoidal, are isomorphic as monoidal categories. And of course, this is a really, really well-known result. But okay, in these monoidal categories, we can talk about really nice objects, which are the algebra objects, or also called monoid objects, which will resemble the notion of a K algebra, where K is a field. So an algebra in a monoidal category is an object equipped with two morphisms of that category. One, which will resemble the multiplication, and the other, which will resemble the unit of that algebra. So you are asking, you need to ask some conditions about associativity, unitility, etc. So, for example, I just gave an example of monoidal category, Gmod. You can consider the algebra objects inside Gmod. And in that case, these objects are called G-module algebras. Also, for example, in the other example I gave, vector spaces, you can consider these algebra objects, which are simply K-algebras in the classical sense. So a nice result that we have from Montgomery and Cohen from the 84 is that, well, you have these two notions of action of group, representation of a group. We know that over vector spaces, they are the same, but actually over algebras, they are also the same. Meaning that if you take an algebra group, an algebra and a group, you have that the three following assertions are equivalent. Having an object, an algebra object in the category of G modules is the same as being in that category and also satisfying these two conditions, which are the formulaic conditions we all have seen, which also is the same as having a group homomorphism from G to the group of algebra automorphisms of A. So for being a module, you can guarantee that the group homomorphism goes from G to GLA, to the linear general space of A. But in this case, you actually are landing in the group of algebra automorphisms. So it's more specific. That's the difference here for algebras versus vector spaces. So with this theorem, I have shown that for a group and an algebra, acting categorically, meaning that you are an algebra object in that category, is the same as acting representation theoretically, meaning that you have this type of map that I was having here in this theorem. Something going from G is a group, so it has to be a group homomorphism from a certain subcollection of the linear automorphisms of A. That will be a representation theoretical in this case. So a natural question is, which other algebraic structures have this behavior? So let's go towards Hopf. Let's try to consider something more Hopfish. So for a group, consider the group algebra. The group algebra is actually a Hopf algebra. So of course, since it's an algebra, you can consider the category of KG modules, which is actually obtained by linearizing the actions of the original group. So in the end, that's just saying that KJ mode is monoidally equivalent to G mode. But in this setup, we get 4 functors. Well, actually 3, but one of them is double, meaning that you can consider the group algebra functor. That will be the functor going from the category of groups to either the category of algebras or the category of Hopf algebras. You can land in those two algebras. So we could say that we have 2 different functors. You also can consider the group of units that takes an algebra and gives you the group of invertible elements. And finally, you can consider the group of group-like elements functor, which takes a Hopf algebra and gives you the group of group-like elements. So what is nice about these 4 functors is that actually they lead you to adjunctions. So for example, that functor that was taking a group and giving you an algebra is a left adjoint to that functor that takes an algebra and gives you the group of invertible elements, meaning that in the end, you have this natural bijection here. And something similar happens when you replace algebra with Hopf algebra. But in that case, the adjunction is not with the group of invertible elements, but with the group of group-like elements of the Hopf algebra. So what's the importance of this result? Well, basically, the importance of this result is that it allows you to extend what you had for the group G to the group algebra KG. So we have this result, which is just putting in one result all the things we had before, that says the following. It's equivalent to have a G module and a KG module algebra Well, yes, because in both cases, it's having an algebra object in these categories, and these categories, as I mentioned before, are monoidally equivalent. So it respects algebras. And in the Cohen-Montgomery result, we have that 2 and 3 are equivalent. Having this map here is equivalent as having a modular algebra over G. But what the adjunctions of the previous slide gives us is that you can extend this group homomorphism from G to the algebra automorphisms of A to these group algebras here, which is nice. And of course, using the bijection, you get a Hopf algebra map between these two objects. So what we have proven is that having an algebra object in the category of modules over Kg over the group algebra is the same as having a map from Kg, which is a Hopf algebra, so you need to have a Hopf algebra map, to certain object which has the same structure as Kg and depends on the linear automorphisms as subcollection of linear automorphisms of A. So again, this equivalence appears here. So let's try to generalize this to a broader setup. We call an algebraic structure Hopf-like if its category of modules or comodules is monoidal. So examples of Hopf-like structures are, as I was just mentioning, group algebras, but also you have Lie algebras, enveloping algebras of Lie algebras, classical Hopf algebras, but also things that are not Hopf in the classical sense. Groupoids, groupoid algebras, Lie algebroids, weak Hopf algebras, and Hopf algebroids. So you have a broader collection than that of Hopf algebras. So formally, what I was mentioning before, acting categorically on an algebra will be just saying that the algebra is an algebra object in the monoidal category H mod. So that's acting categorically. And acting representation theoretically is saying that you have a map that goes from H to a collection of linear endomorphisms of A that admits the same structure at H. For example, if I'm talking about Lie algebras, I want a Lie algebra map going from the Lie algebra to something that is a Lie algebra obtained from a subcollection of linear endomorphisms. In the case of linear maps, excuse me, of Lie algebras, sorry. In the case of Lie algebras, the object here will be actually the derivations of the algebra, which is also a well-known result. So what are our results? In our results, we have proven in a work soon to be published on the archive that a Hopf-like structure acts categorically on A if and only if H as categorically representation theoretically on A for the following H. So for groups and group algebras, that's well known. For Lie algebras and enveloping algebras of Lie algebras, that's well known. I'm just mentioning here to have everything in one list. But we also did it for commutative Hopf algebras, which in this case was not done. For groupoids and groupoid algebras was also done. For some Lie algebroids and enveloping algebras of some Lie algebroids, some Lie-Reinhardt algebras, and for some co-commutative with Hopf algebras, we did this work of proving this equivalence between the categorical word and the representation theoretically word. This was a joint work with Hondi Huang, Elizabeth Winks, and Robert Wong from the US. And I want to show you one specific case of all this. Unfortunately, I don't have the time to show all the cases, but I want to show you what we did with co-commutative Hopf algebras. So for that, I need to recall what's the smash product. So take a group and take a Hopf algebra. And assume that for some reason, you know that Hopf algebra is a Kg module algebra. It's an algebra object in the category of Kg modules. Since it's a module, you know that there exists a group homomorphism going from G to the group of algebra automorphisms of H. But you could ask additionally that actually the image of pi doesn't land here. You could ask that the image to land in the group of bialgebra automorphisms of A, which is which is actually as the same as asking each component of pi to be a coalgebra map. In that case, you can form what we call the smash product of algebra. In general, the smash product is defined in more general conditions. It's just an algebra. But in order to be a Hopf algebra, you need to ask this condition that I was mentioning here. Each component of this action needs to be a coalgebra map. So in that case, you can consider the smash product Hopf algebra, which, if you don't know what's the smash product, it's just this vector space, H tensor Kg, with some flavor on it, some operations that make it a Hopf algebra. So for cocommutative Hopf algebras, these are Hopf algebras that satisfy a nice property in terms of the coproduct. There is a really important classification theorem, which is called the Cartier-Gabriel-Constant-Mignon-Moore theorem. A lot of people in there, that says the following. If you take a cocommutative Hopf algebra, then you can actually characterize that Hopf algebra by saying that this H is isomorphic to the smash product of an universal enveloping algebra of a Lie algebra and a group algebra. And actually, this Lie algebra and this group are very specific constructions, not any group or any Lie algebra. But as it says here, the Lie algebra is that of primitive elements, and the group is that of group-like elements of H. And G acts on the Lie algebra by conjugation, and that means that actually this is indeed a Hopf algebra, using what I mentioned in the previous slides. And of course, this is only true if you are taking an algebraic closed field of characteristic 0, so I am assuming that here. So the moral of this slide is that if you take a cocommutative Hopf algebra, that's just this. It's the tensor product of a universal enveloping algebra with a group algebra with some flavor on it. So we prove, as I was just saying, that these cocommutative Hopf algebras satisfy this equivalence. Acting categorically is the same as acting representation theoretically, which means the following. Well, I need to present the result, but for that, I need just another definition. Take two rings, R and S, with a ring homomorphisms between them. You also take a module over R and a module over S. So we will say that a group homomorphism going from M to N is a linear homomorphism over beta if it satisfies this condition over here. Just a technical definition that will appear in the next result. So this theorem, which is one of the many we prove, says the following. Take a cocommutative Hopf algebra, which by the theorem I mentioned is just a smash product of UG with KG for some group and some Lie algebra. Take an algebra. So saying that that algebra is a algebra object in the category of modules over H, which is just saying that it is an H module algebra, is the same as having two homomorphisms, one of groups and the other of Lie algebras, between G and this object and the Lie algebra and this object of derivations, which actually can be extended to be Hopf algebras homomorphisms between KG and this group algebra and between UG and this universal enveloping algebra of the derivations, which is actually the same as saying that you have a Hopf algebra homomorphism between H and this smash product, which is again a Hopf algebra, and of course, since it's a smash product, is cocommutative again. So we prove that in the cocommutative Hopf algebra setting, the correct gadget to put here in the representation theoretical setting is this Hopf algebra here. And actually, just to give you a heads up of the other things that will appear in this paper, will be published on the archive probably by Friday. We did it with these other structures by putting here the correct endomorphism structure, we call it. So for groups, as I just mentioned, was the algebra automorphisms of the algebra. For the group algebra, is just taking the group algebra of that. For the Lie algebras, is the derivation of the algebra. For the enveloping algebras, is the universal enveloping of that Lie algebra. And as I mentioned in the previous slide, for cocommutative Hopf algebras, is this smash product. So for the weak cases, we also did it. weak cases, I mean weak Hopf algebras. So for questions of time, I'm not giving the definition here, but we also did it for weak Hopf algebras, for some Lie algebroids, and for groupoids and groupoid algebras. So that's it. Thank you very much.
Right. Are there any questions? All right, if there are no questions, let's thank the speaker again.
Thank you.
And we'll make some breakout rooms. So if you think of any questions later, you can discuss